In this new section, we're going to talk about normal random variables. Normal random variables. We say that X is a, in shorthand, normal random variables, or simply X is normally distributed. You'll hear that a lot. X is normally distributed with some parameters. And we've seen these parameters before, with parameters mu, the mean, and their standard deviation. Okay, so when we say that X is normally distributed parameters, if the probability distribution function of X is given by this. So depending upon how the PDF is given, either uniformly you have a uniform distribution, you have a normal distribution, every geometric distribution, etc. And f of X is times sigma times e to the negative x minus mu squared over 2 times sigma squared. The graph of this PDF is a bell-shaped graph where the center is mu. It's symmetric about mu. In other words, what's to the left of this line is the same to the right. You're at the top. You go a little bit to the left, you go the same amount to the right, it's symmetrical. They both yield the same height. You go this much to the left, you end up here. You go that same amount to the right, you end up here. They're both at the same height. It's symmetrical. If you put red paint, say along here, that's blue. If you put red paint along here, nice and thick red paint, and you folded along this, you folded the paper along this line, or in my case, a board, that red paint will end up right on here. Symmetrical. And the graph should not have gone below down here. This is distribution. PDF is that complicated looking function. I guess I should have said that X can go from negative infinity to infinity. Now let's show that this is real. It must be the case that if you take 1 over 2 pi square root sigma e to the negative x minus mu all squared over 2 sigma squared, and you integrate this from negative infinity to infinity, you should get 1. Now, let's actually verify this. Well, first, I'm going to let u equal x minus mu over sigma. Oops, let u equal that. So then du, and just keep in mind this is x over sigma minus mu over sigma, and dividing by sigma is the same as multiplying by 1 over sigma. The derivative of a constant times x is just the constant, minus mu over sigma is just a number. The derivative of a number is 0. So du will just be 1 over sigma dx, or multiplying both sides by sigma, you get sigma du is equal to 1 times dx or dx. So let us make these changes. We have the integral from negative infinity to infinity, 1 over 2 pi sigma e. Now, we can think of that power as negative x minus mu over sigma all squared, but let's not forget the half. You get negative 1/2, and what's inside the brackets is exactly what we are calling u. So 1/2 u squared. Oops, I forgot to write dx at the end. So I wrote this down. I wrote this in the u language. I'm going to write that in the u language. dx is sigma du. I will put the sigma in front of the int. Oops. Okay, sigma du. And it turns out that the sigma, so that's a square. Okay, so I'm going to get rid of my u substitution work because I need this space. The 1 over 2 pi, I'm looking over here now, the 1 over 2 pi, 1 over the square root of 2 pi, I can factor out. And we need to integrate e to the negative u squared over 2. Multiplying by a half is the same as dividing by 2. Okay. du. Now, how are we going to do this? So now, again, I want this integral to equal 1. Well, what do you multiply? 1 over the square root of 2 pi times this integral should equal 1. So it remains to show that this integral, e to the negative u squared over 2 du, should equal to the square root of 2 pi. Because if you multiply 1 over the square root of 2 pi times something and you get 1, that something will be the square root of 2 pi. This integral should be the square root of 2 pi. Now, I want to say one other thing. We know that x goes between negative infinity and infinity. Well, if you just take away some constant, it's still going to go between negative infinity and infinity. And if you divide it by some number, either it'll go to these infinities a little bit faster, or a little bit slower, or even a lot slower. But nonetheless, it's still going to go between negative infinity and infinity. So the limits, coincidentally, do not change. We need to show that that integral from negative infinity to infinity is the root of 2 pi. Okay. Put that on the top because I need some more space. Okay, we must show that the integral from negative infinity to infinity of e to the negative u squared over 2 du is the square root of 2 pi. Now, what I'm about to do is very standard for this type of integral. I'm going I. I'm going to let I equal this integral. Negative infinity to infinity of e to the negative, well, I'm going to change my letters. It's alphabet soup. I'm going to replace u with x. I'm going to say that. Okay? Now, I squared will equal to this integral times itself. The integral from negative infinity to infinity of e to the negative x squared over 2 dx times itself. But like I said, the letters don't matter. Now, instead of using x's, I want to use y's. Y squared over 2 dy. This is the same as the double integral. They both happen to have the same limits. Negative infinity to infinity, negative infinity to infinity. E to the negative x squared over 2 times e to the negative y squared over 2 times dx times dy. Dx, dy. We're making progress now, because this here is nothing more than a double integral from both limits negative infinity to infinity. In multiplication, if the bases are the same, you can keep the base and add the exponents. When you add the exponents, you get negative x squared plus y squared over 2 dy dx. And the limits are both negative infinity on the bottoms and infinities on the top. Now, what we're going to do now is, let me get rid of this please, is we're going to change to polar coordinates. When you want an answer that have pi's in it, probably go to polar. Let me write it down up here. You have that x's are cosine theta, and y is r sine theta, and that dy dx is r dr d theta. I'm not going to prove this. You learned this in Calc 3. Okay, so I squared, let me actually write it. I squared equals the double integral. Now, when it comes to this, x squared plus y squared is r squared. I mean, if you square x, you get r squared times cosine squared theta. If you square y, you get r squared sine squared theta. Well, if you have r squared cosine squared theta plus r squared sine squared theta, and like I said, this is x squared plus y squared. In the right-hand side, you can factor out the r squared, and you're left with cosine squared, a plus sine, and then a sine squared. But what's in that bracket is 1. R squared times 1 is r squared. So yes, x squared plus y squared is really r squared. So right there, I'm going to put r squared. You get e to the negative r squared over 2 times dy dx becomes r dr d theta. That's one of the substitutions I said we're going to use. And now the limits. The only thing is I prefer to change the order of integration. So I'm going to do d theta first, then dr. And it's going to that theta goes from 0 to 2 pi. Theta goes between 0 and r is going to go from 0 to infinity. Think about why those limits make sense. I have to leave you with some things to think about. You have x squared plus y squared. You have x squared y which of course is a circle, and x and y are getting bigger and bigger. So the circle is going to get bigger and bigger. That is why the radius first is 0 and then it goes out to infinity. That is why r goes from 0 to infinity. And if you want to cover everything, you should go, I'm giving you the answers why the limits are. You go from 0 all the way to 2 pi. Go from theta equals 0 to theta equals 2 pi. Then you get the whole circle. That is why it's that. Okay, but now this integral in front of us, we can do this one. We can do this one. You know, we can do this with respect to theta. This is a constant. Has theta in it. So it's integral, copying the first integral, and with the limits, integral from 0 to theta, 0 to infinity. The integral of a constant times theta is just theta, from 0 to 2 pi. Well, I do have a little typo. The integral, actually more than a typo, I said it wrong. The integral of a constant times d theta is the constant times theta. And theta goes from 0 to 2 pi dr. Okay, so we're going to evaluate this. First, I plug in 2 theta for pi. Sorry, I plug in 2 pi for theta. The integral is 0 to infinity of e to the negative r squared over 2 r times 2 pi minus, and then you plug in 0 for theta. If you think about it, this mess times 0 will be 0. Let's get what I wrote so far. Times dr. It's a typo there. It always was dr. Sorry. Times is a constant. I'm going to bring it in front. It's 2 pi times the integral of e to the negative r squared over 2 times r. And make a substitution change. Let u equal negative r squared over 2. Well, then du, bring down the power, will be negative 2r over 2 dr. The 2's cancel. Okay, that is, we get negative r dr. You want to divide by the negative 1, fine. What you can do is, you can put in a negative sign, so long as you bring out a negative. So, coming up here, we have negative 2 pi in front. And this piece will be e to the negative u. Nope, u was negative r squared. It will be e to the u, and negative r dr is du. The thing is, I know that integral. The integral of e to the u du is just e to the u, where u happens to be negative r squared over 2. And I'm supposed to go from 0 to infinity. 0 to infinity. Let's do this on top. Just remember, we are, well, let me not erase so much. That's what the OK was for. Remember, we are solving for I squared, and in the end, we want I to be the square root of 2 pi. Maybe I'll just do it here. And that negative sign, I hate it, so you know me, I changed the limits. So we have 2 pi e to the negative r squared over 2, and we want to evaluate it from 0 to infinity. But we can't plug in infinity. We call it k, and then we take the limit as k goes to infinity. Well, let's first find out what this is. We'll take the limit at the very end. When you plug in k, you get 2 pi. Now, since that's a negative exponent and it's in the numerator, I'm just going to put it in the bottom. But r becomes k. Minus, same deal, 2 pi over e to the 0 squared over 2. 0 squared is 0, divided by 2 is 0, e to the 0 is 1. This whole mess is just 2 pi. And, remember I said I was going to switch the limits? I never did. It should go from infinity to 0. How come that didn't erase? But instead of infinity to 0, we will go k to 0. So the big deal is, first I should have plugged in 0. And for the same argument just given, this will be 2 pi. And in the other one, I should have plugged in, let me erase the whole thing. I should have plugged in k. So it is 2 pi over e to this k squared over 2. Okay. This is just 2 pi. As k goes to infinity, it doesn't care about, 2k doesn't care about it. As k changes, 2 pi is a constant, minus. K is infinity. Infinity squared is really large. Divided by 2, it's still very large. E to the very large is very large. 2.718 times itself time and time again is very, very, very large. And if you just have 2 pi and you divide it by very, very large, you get 0. So it turns out that I squared is 2 pi. So I is in fact the square root of 2 pi. And that's what we wanted to show. Because when you multiply 1 over 2 times the square root of 2 pi times that integral, you got the square root of 2 pi, which is 1. That's to show, yes, it's the PDF. The integral from negative infinity, positive infinity, absolutely ends up to 1, or absolutely equals 1. Let's try something else now. Always, or in many cases, we try to find out the expected value and the variance. So let's find the expected value. Remember, the PDF is the integral from negative infinity to infinity, 1 over the square root, 1 over the square root of 2 pi times sigma. The square root is just above the 2 pi times sigma times e to the negative x minus mu squared over 2 times sigma squared dx. That's the PDF. Well, e of x will just have that one change right there. It would just have that one. Now, sometimes you have to be clever about how you think things. And to me, this is a very clear move to make. Instead of x, we're going to think of x as x minus mu plus the mu. Minus mu plus mu is 0. So that gives us two integrals. You have, first, instead of x, you have x minus mu. 1 over 2 pi square root sigma e to the negative x minus mu squared over 2 dx plus just mu. The x is now just mu. Integral of mu times 1 over the square root of 2 pi sigma e to the negative x minus mu squared over 2 sigma squared dx. From negative infinity to infinity on most of these integrals. Okay. The reason to do this is this mu can come out in front. And we know this integral. It's 1. Mu times 1 is mu. Okay. So it's plus mu. Okay, now first thing I realized is I didn't know how to do this. I didn't know how to do that until I said, let me break it up so I do know. So I do know at least one of the integrals. This one I know is just mu. Because what's in that big circle? Just 1. Okay. And the second thing is I said, you know what? I can get rid of those. I can call it something else. I can call it y. So I call that y, and I call that y. And if y is just x minus mu, then dy is just dx. That is, I can call that dy. And once again, if x goes to infinity, you take away mu, you still get infinity. That is, the upper limit should stay infinity. Y should be infinity. If x is negative infinity and you take away mu, you're still negative infinity, which equals y. Y is negative infinity. So we have y, just recopying this, except instead of x minus mu, I write y, 1 over 2 pi square root times sigma e to the negative y squared over 2 dy plus okay. Now, this here is an odd function. This is an odd function. Odd functions tend to look like this. Whatever you have to the right of 0, to the right of x equals 0, say it's that. What you're going to have to the left of 0 will be the mirror image, but it'll be down here. That is, when you integrate this, it's going to be 0. If all of this area to infinity was negative 700, to the left of 0 all the way to negative infinity is negative 700, well then, to the right of 0 forever will be positive 700. This integral is 0. Okay, the alternative is you integrate it. You actually do the integration. You don't notice that it is an odd function. You really, really, really should recognize odd functions. Again, negative 7 or positive 7, this piece won't care. That will have a sign change. In other words, if you plug in 7, this might be 15. You plug in negative 7, you're going to get negative 15. If you 11 for y, make believe for argument's sake, this is 99. You plug in negative 11, you'll get negative 99. It also could be possible, not in this case, but for other odd functions. If you plug in 3, you might get negative 20. Well, then if you plug in negative 3, you'll get positive 20. The signs will always be different. When you integrate from negative a to positive a, from negative 11 to 11, or from negative 83 to positive 83. If it's an odd function, you're going to get 0. One thing, when you have 0 and you add mu, you get mu. That is, the expected value of a normal random variable will be mu, which makes sense because it's symmetrical about mu. Sometimes you'll get a little bit less than mu. Sometimes you'll get a little bit more than mu. Sometimes you'll get a lot less than mu. The same number of times, you'll get a lot more than mu. Sometimes you'll even get mu. In the end, the average will be mu. To find the variance, it's been a long time since we used this alternative formula, but we know that the variance of x is the expected value of x minus the expected value of x, the whole thing squared. But we now know that that's mu. E of x is mu. The expected value, the variance of x is simply the expected value of x minus mu squared. The expected value of x minus mu squared. Okay, so that equals the integral from negative infinity to infinity of what you're taking the expected value of, x minus mu squared times 1 over the square root of 2 pi times sigma times e to the negative x minus mu squared over, 2 sigma squared. And what you should let y equal x minus mu over sigma. So then dy will be 1 over sigma dx, or multiplying both sides by sigma, we get sigma dy is equal to dx. And once again, if x is infinity, infinity minus mu is infinity, divided by sigma, what you get will still be infinity. Same thing for negative. That is, the limits are not changing. Negative infinity to infinity. I will pull out the constant 1 over the square root of 2 pi sigma. So that was pulled out. This here is y squared. Well, actually, that's not true, because sigma y is only x minus mu. It's sigma squared y squared. I pulled this out, and this here is e to the negative. There's the 2 on the bottom. But x minus mu squared over sigma squared is nothing more than x minus mu over sigma all squared. But that's y inside there. It's y squared. Let's get rid of our side work. And like it should have said, times dx. And dx is sigma dy. Sigma times, I will cancel this sigma with the 1 in the bottom in front. So I have, and I'll even factor out the sigma squared there. 1 times sigma squared divided by the square root of 2 pi times the integral negative infinity to infinity y squared e to the negative y squared over 2 dy. Y squared and not y. I would suspect that this would be an integration by parts problem. We have the front factored out, 2 pi, excuse me. now times this. But using parts, and I'm not actually worked this out beforehand, I'm not going to do parts. This is a probability course. It's y e to the negative y squared over 2 from negative infinity to infinity plus the integral of e to the negative y squared over 2 dy. Also from negative infinity to infinity. Once again, this is odd. Let me think for a second. Well, sorry. It's the integral of dy. Well, this is an odd function and it's going from negative infinity to infinity, so you get 0 again. So we have sigma squared over the square root of 2 pi times times this integral. But we just did that integral. We just did that integral earlier. That's I. This integral was what we called I earlier. And we discovered that that equals the square root of 2 pi. So we get sigma squared. The variance of the random variable in a normal distribution is sigma squared. That's the variance. What a surprise that the variance had to do with sigma. The variance is sigma squared. The standard deviation is sigma. And this section on normal random variables.